Good afternoon. I'd like to do right now an overview of classical physics. That's a necessity in order to discuss modern physics. And while we might have done some of this before, we'll start from the beginning. The beginning being, of course, the Big Bang. That was a long time ago. But when did people start doing classical physics? Classical physics really started with, you could say, definitely there's been records of classical physics in the ancient times, in the with the ancient Greeks. Actually, even earlier than that, the ancient Egyptians tried to describe why things happened, but they often referred to the gods, of course. And then you've got the ancient Greeks, which, whoops, the ancient Greeks, which is, BCE. They described getting a little stuck up here on my pad. I'm just going to go ahead and fast forward it, and then we'll talk about that. So let me start again. So the ancient Greeks, ancient Egyptians and ancient Greeks, in many hundreds of years BCE, thousands of years BCE, described physics, but they referred often to the gods and didn't have the scientific method down. Of course, in ancient times, it was the Greeks that had the first university and really started sitting around and thinking about things and trying to solve problems. But it wasn't until the Middle Ages, around 1000, whatever CE stands for, I'm blanking on it, before CE and CE, around 1000, that the scientific method really came about, and it was really the Muslim academics from in the 800s to 1000s that really pinned down the scientific method and started using the scientific method. But there was still a lot of physics that was not well understood, and it really wasn't until modern times, and I mean modern times meaning in terms of over the ages. Modern times are approximately 1600 to now, that people really started using scientific method and really started explaining the physics of what's going on, how the world works, right? What is physics? Physics is the way things work. So, so what we're discussing when we're talking about classical physics, built on the ancient Greeks, built on the Muslim academics, but really came about in the modern era from 1600 to 1900. So during that era, of course, you've got people like Newton. Prior to Newton, you've got Galileo, who did much of the modern physics of motion and forces. But Newton, Galileo, Huygens, Young, those are the people who many of the names in classical physics. Classical mechanics, and of course in electricity and magnetism. You've got Gauss and Coulomb and Ampere and Maxwell, who put it all together. We've already discussed some of this. So the classical physics are these names, and I just want to do a little review of classical physics, right? We start with Galileo, who describes motion, and Newton, who on top of that describes dynamics. Galileo certainly did a lot of the kinematics and dynamics, but Newton did forces and energy and momentum. And Huygens started discussing waves prior to Newton. Newton, of course, one thing that people often forget is some of his biggest work was in optics. So Newton described classical optics, ray optics, right? Ray tracing. And Newton was the first, well, not the first, I'm sorry, but Newton also discussed corpuscular theory. Corpuscular theory is looking at light as a particle instead of as a wave, which is one of the primary things of quantum mechanics. But so we start with kinematics and F equals ma and P equals mv and F. I guess I should be writing some of these things down. Some of the classical mechanics that you should remember, you should have a feel for. You may not have all the details in your head, but the kinematics and dynamics, conservation of momentum, conservation of energy, optics, ray tracing, geometrical optics. This is all classical physics. And waves, right? Waves. Whoops, that's a little messy. Waves. Waves. What are waves? You know what waves are. You should know what a wave is. Give you a second. What is a wave? Pause, pause, pause. A wave is a disturbance that travels in a medium. A wave transports energy but not matter from one place to another. What is a property of a wave? Waves reflect, diffract, and interfere. If you don't know what this means, right, you know what reflection means. Diffraction, they spread when they go through an opening. Interference means that they add or subtract from each other when they're on top of each other. We will actually talk more about interference later on. So that's all classical physics. Really don't teach a whole lot of thermodynamics in these intro physics courses. We touch on it here and there. Hopefully you've learned it in other classes, but it's part of classical physics that was well understood between, in the modern era. The zeroth law of thermodynamics is what defines thermodynamics. It's what defines temperature. It really is just what is it? The transitive property. What is the property? If A is equal to B and B is equal to C, then A is equal to C, right? It says that if A is in thermal equilibrium with B and B is in thermal equilibrium with C, then A is in thermal equilibrium with C, and whatever that thing is that is equal, we call it temperature. So that's the zeroth law. The first law of thermodynamics is simply an energy conservation. It's a statement of energy conservation. If you add heat to an object, if you add heat to a substance, then its energy goes up. If you do work on a substance, then its energy goes up. The first law of thermodynamics is the change in internal energy of a substance is equal to the heat added plus the work done. The second law of thermodynamics is one of the most important laws you could possibly know. I know we've discussed it before. You may not remember it. I hope you do. The second law of thermodynamics says that it does say that heat spontaneously goes from hot to cold, but not from cold to hot. But what's important about the second law is this idea that things only naturally become more disordered. They don't naturally become more ordered. That's the same as saying heat goes from hot to cold. The second law says that disorder always increases. That's entropy always increases, right? The increase in entropy is spontaneous. Entropy does not spontaneously decrease in a system. That second law is super important because it says that not only is energy conserved in a process, but you always are going to lose some energy to some of the energy to some kind of non-useful process. In other words, not all of heat can be changed into work in, let's say, a heat engine or a motor, right? In your car, when you burn fuel, not all of the energy of burning the fuel is going to go into the forward motion of the car. Some is going to go up to heating the atmosphere, and that cannot be stopped. You cannot get a perfect cycle going there, which means there is no such thing as a perpetual motion machine. And if you look in the literature, the opposite of the literature. If you look on the web, you'll see all kinds of people who claim that they can make energy where there is none, that they can have either perfect perpetual motion or even create energy out of nothing. Second law of thermodynamics absolutely says that can't happen, and the second law of thermodynamics is one of the most well-proven laws in all of science. The third law of thermodynamics says it's not possible to get to T equals 0. There's a lot of things that you conclude from that. For instance, you can't stop the motion of all objects. But T equals 0, it's not possible to get to a temperature of absolute 0, right? So on the Kelvin scale. And that has a lot of consequences in science. So there's a lot more to thermodynamics, but those four laws are very, very fundamental to all of the physics that we do. Moving from thermodynamics, electricity and magnetism, physics 116 stuff, where we start with the concept of charge and the fact that you can calculate the field from a charge using Coulomb's law, right? So Coulomb is one of the names. And then we move to Gauss's law, where Gauss has a better way, or perhaps an easier way to calculate the electric field from a collection of charges. And then we move from Gauss and Gauss's law to the force on a charged particle, or the Lorentz force. Lorentz is somebody else who looked at electricity and magnetism. And then we move to magnetism, where we calculate the magnetic field from currents, and that's the Biot-Savart law. And then Ampere comes along and tells us how to more easily, like Gauss, calculate magnetic fields from collections of current elements, or currents running through wires, charges moving through wires. And so you got Gauss's law and Ampere's law, and then you've got Faraday, who tells us one of the most important things we could possibly know in all of electricity and magnetism. Faraday shows us that moving magnetic fields, in other words, changing magnetic fields, create electric fields, and that's how we generate current in wires. We can actually create electricity by moving magnets near wires. And that's all about how two electric charges exert forces on each other, but a charge and a magnet do not exert forces on each other. Two magnets exert forces on each other, but again, a charge and a magnet don't exert forces on each other until a charge is moved. Once a charge is moved, because a moving charge is observed to exert a force on a magnet, then a moving charge must be a magnet. And from that, we can actually conclude that moving magnets must make charges move, because they will exert forces on stationary charges. Moving magnets must exert forces on stationary charges. So you move a magnet, you create an electrical current. Ta-da! We have created electricity, one of the most important discoveries in all of electricity and magnetism of all time, Faraday's law. We couldn't have this recording that you're listening to. You couldn't have the computer. You couldn't have the lights. You couldn't have the phone. You couldn't have just about anything that we have today in terms of modern technology without the generation of electricity. That's Faraday's law. So I'm going to write down these basic laws, because it was then, and where we're going with this, because we've already discussed this, is that James Clerk Maxwell, took these laws that we're talking about, the laws of E&M, and put them together in such a way that he showed that they're very compact and they all relate to each other in some ways. Really important for you to remember from Physics 116, Gauss's law. So that's the first of one of Maxwell's four equations, basically. And Gauss's law tells us that the electric flux, remember what's on the left-hand side here is electric flux, through a closed surface is equal to the charge enclosed by that surface divided by a constant. So with Gauss's law, remember we can have, let's just start with the simple. We have a single charge Q, and we put some kind of Gaussian surface around it. That's a three-dimensional surface. And we can say that the electric flux, right, the field lines that go through that surface, is equal to the charge enclosed divided by a constant. And that allows us, that actually tells us a lot of information about the electric field or various other properties of electricity and magnetism. That's Gauss's law. Then Ampere's law is the analogy of Gauss's law in magnetism, right? So Ampere's law we used it to calculate magnetic fields due to current distributions, like Gauss's law is to calculate electric fields from charge distributions. So we have this quantity on the left, which is not flux. It is the line integral of B through a closed loop instead of flux, which is the E dot dA, which is the surface integral. The hard way of putting it is the surface. So the E dot dA is surface integral of E over a closed surface. That's just the electric flux. It's easier to think of it if you know what flux is. B dot dl is a little harder to describe in a simple way. But in any case, let's just pretend we have some kind of current. This is an electrical current going through a wire. Electrical current going through a wire. Simplest form, we can take an Amperian loop, right? We can put a loop. This is a two-dimensional thing because it's got an area. It's got a, well, whatever. It's a one-dimensional line looped around the wire. And if we take the integral of B dot dl, dl being the length of the loop around the dotted loop, that is equal to some constant, mu zero. So some constant times the current enclosed. The current enclosed in this case is a single wire with current I. So we integrate B dot dl around that dotted loop, and we can relate that to the current enclosed in the loop, and that allows us to, for example, calculate magnetic fields. You would have to look back at Physics 116, how we did that. But Ampere's Law is something you should be familiar with. For calculating electric and magnetic fields, we're not going to look at the Beer-Savart law or the Coulomb's law because these really encompass those two laws. So we'll move on from these to Faraday's law. Now remember what Faraday's law was. Faraday's law said that Faraday's law said that the potential difference, delta V on the left, is potential difference. Is in a wire or some kind of circuit is given by the time rate of change of the magnetic flux. There's a negative sign that just tells you about the direction, really, of the current that's produced. But this is Faraday's law, that the potential difference is equal to minus the time rate of change of the magnetic flux. So what we do in Faraday's law is we remember that delta V, the potential difference, remember that delta V has to do with an electric field, right? So delta V is E dot dl. This does have to be a closed circuit, so it will be a closed loop. And flux, magnetic flux, is the integral of B dot dA. So this Faraday's law, this law, can be rewritten with these two substitutions to be. So this is Faraday's law with that substitution. So you can see here, let me go back here a second. Yep. So you can see here that we've got a relationship that we hadn't seen before. It's a relationship between magnetic fields and electric fields. And look at this, right? This is a time rate of change. If you change the magnetic flux, you induce an electric field. Changing magnetic fields induce electric fields, or changing magnetic flux, that's the same as changing the field, or you could just change the field and you'll change the flux, induce electric fields. Well, in the same way, so these three equations are what Maxwell was working with. There's a fourth equation. Let me just do that real quick as an aside. The fourth equation, and then I'm going to come back to this because this relationship is really important. The fourth equation that Maxwell was working with is called Gauss's law for magnetism. Remember that Gauss's law for electricity, which we only called it Gauss's law because it was the only Gauss's law we knew, said that the electric flux through a closed surface is equal to the charge enclosed divided by a constant. That's a really important concept. Sorry, I'm pointing at it without you seeing it. The electric flux through a closed surface is equal to charge enclosed in the surface. And the constant is inconsequential. It's just divided by a constant. So Gauss's law for magnetism should relate the magnetic flux through a closed surface. So I'm going to do B dot dA. Don't worry about the fact that we just have that in Faraday's law above. This has nothing to do with that right now. And the arrow is not relating these two either. So let's just get rid of that. Okay. This is independent. Okay, B dot dA, the magnetic flux through a closed surface, is equal to the magnetic charge. What does that mean? I have no idea. But the magnetic charge enclosed divided by a constant, right? The constant's inconsequential. So that's what Gauss's law for magnetism says. But what is magnetic charge? What is magnetic charge? Well, think about this for a second. Magnetic charge is just, right, a north pole or a south pole, right? So let's take a magnet and put it, that's just a north-south magnet, and put it inside a Gaussian surface. I'm just going to make my Gaussian surface red. How much total magnetic charge is enclosed in that surface? how many net north or south poles, right? Total electric charge is how many more plus charges do you have than minus charges, how many more minus charges do you have than plus charges. For magnets, I'm just going to give away the answer. Hopefully you know it. For magnets, you can never have more north poles than south poles. For every north pole, there's a south pole. That's sort of the definition of a standard magnet, that you can't cut a magnet in half and have just one pole. So what is the net magnetic charge of this, at least in this situation? The net magnetic charge, Q magnetic, is equal to 0. In other words, what I'm really saying is that you can never encompass a net magnetic charge. You're always going to encompass a net magnetic charge of 0 because every north pole has a south pole associated with it. You can't separate poles. There are no magnetic monopoles. So I just wrote it down. There's no such thing as a magnetic monopole. You cannot have a net magnetic charge. That means that we can simplify Gauss's law for magnetism to look like this. B dot dA equals what? Equals 0. And that is the fourth of Maxwell's equations. I'm going to go back. 1, 2. Remember, the third was just Faraday's law, which I rewrote on the other page. Third and fourth. Now, let me say one more word about Gauss's law for magnetism. There's nothing in physics that actually says we cannot have a net magnetic charge. It is just our understanding of magnets right now. You might have read articles about these really weird systems where they think they've detected monopoles, and there is no reason why we can't have monopoles. And if we did have monopoles, we would just modify Gauss's law for magnetism. Instead of being the equation on the bottom, it would just be an equation that would look like this. If we do indeed have monopoles, which we might have. But for now, we typically, at least in a classical system, in a typical system, we have no monopoles. And so the net charge enclosed is going to be 0. That's all I'll say about that. So let's just summarize where we are right now. So this is a summary of Maxwell's equations as we just discussed them. And you might ask, does that include all of electricity and magnetism? The answer is it really does, except for one thing. Well, except for two things. Anything that we've done in electricity and magnetism, anything we've discovered in electricity and magnetism is really encompassed in these equations except for the Lorentz force. The Lorentz force, so these are relationships between magnetic fields and magnetic charges, electric fields and electric charges, fields and moving charges versus stationary charges, right? That's what these are about. But the Lorentz force is the force on an electric charge in an electric field or a moving charge in a magnetic field, right? Remember that stationary charges do not feel forces from magnetic fields, but moving charges do feel forces from magnetic fields. And remember what that force is, it's QV cross B. So this is the Lorentz force. So now what we have on the page encompasses all of electricity and magnetism except for Maxwell's improvements. There's one additional thing we have to do. So again, I'm going to say it one more time. Everything on this page encompasses everything we've done in electricity and magnetism, believe it or not. And I wrote down the first four equations without Lorentz force only because the Lorentz force is not necessary to understand what power Maxwell had with these four equations. Lorentz force is just another equation. But those four equations are what's called Maxwell's equations. Lorentz force is not one of Maxwell's equations. Okay. This takes us up to classical physics in the end of the 19th century. In our next lecture, I'm going to talk about what Maxwell did with these equations, etc. But up until now, we just did up until Maxwell put together the equations. This is basically all of classical physics that was understood until Maxwell came around, did what he did, and Einstein came around and tried to fill the gaps.